Logo of the National Center for Advancing Translational Sciences, June 8, 2020. Text: Joni Rutter, PhD, Deputy Director, National Center for Advancing Translational Sciences, National Institutes of Health. Dr. Rutter stands on her porch, speaking into the camera.
Hello, my name is Joni Rutter, and I'm the Deputy Director at the National Center for Advancing Translational Sciences, also known as NCATS. Today, I'd like to introduce you to an exciting new program that we're launching related to COVID-19. As you well know, we're in the midst of this pandemic, and currently there are no FDA-approved treatments and no standardized way to collect real-world clinical data that could inform research and eventual clinical care practices. That's why NCATS and its partners are establishing N3C, or the National COVID-19 Cohort Collaborative. Here, speed is critical. N3C is developing the means to rapidly collect and harmonize clinical, laboratory, and diagnostic data from hospitals across the country to address not only the current and immediate needs of COVID-19, but also the long-term health consequences of COVID-19 in the population. So far, more than 20 organizations have agreed to contribute data to N3C, and the initial data has been ingested and uploaded. More data sets are coming and will be added as they go through the transfer process. N3C has some innovative and unique features, especially around the analytics framework. And what you'll see in the demonstration video gives you a first look at the types of data and analyses that users will be able to access to answer all sorts of critical questions about treatments, about risk factors, about health outcomes, and other COVID-19 related questions. So take a look.
Text: presented by Christopher G. Shute, MD, Dr. PH, Bloomberg Distinguished Professor of Health Informatics, Professor of Medicine, Public Health, and Nursing, Chief Research Information Officer, Johns Hopkins Medicine Deputy Director, Institute for Clinical and Translational Research, Johns Hopkins University.
My name is Chris Shute from Johns Hopkins University, and along with Melissa Handel, I co-lead the N3C.
Slide. Heading: Phenotype and Acquisition. Text: Dual Purpose Workstream. 1. Work with the community to write and maintain a computable phenotype for COVID-19. 2. Write and maintain a series of scripts to execute the computable phenotype in each of 4 common data models: OMOP, I2B2 ACT, PCORNet, and Trinetics. Below the text, a flowchart describes the process by which COVID-19 data is acquired, phenotypes are defined, data is run through quality checks, data is extracted and converted to a compatible format, and resulting files are transmitted to the N3C. Text below the flowchart reads: Support is available for all parts of this process at covid.cd2h.org/phenotype and covid.cd2h.org/phenotype-wiki. All specifications and software are shared on GitHub.
We welcome contributions from all sites, especially CTSA sites, where we try to make the process as easy as possible. Specifically, we'll accept data from any common data model, including OMOP, ACT, PCORNet, or Trinetics. We've worked to make the phenotyping extraction process easily done with scripts, with lightweight data quality checks, and extraction code that will transform the data into the zip files for transmission.
Slide. Heading: Common Data Model Harmonization. In the top left, a zip folder has arrows pointing outwards to logos for Odyssey, PCORNet, the ACT network, and Trinetics. In the top right, there is a data table from the modified Odyssey data quality dashboard. Text below the figures reads: First stage ingestion. Unpack zipped CSV files. Check data manifests. Reconstitute into native CDM formats. Hybrid data quality checks adapting Odyssey data quality dashboard.
Once we receive the data, we reconstitute it into the target data models as depicted. We've also adapted the data quality dashboard from Odyssey and merged data quality checks from all of the data models to create an N3C specific data quality dashboard. All of the data that we learn from the dashboard will be returned to the sites to improve the process continuously with data refreshes.
Slide heading: Data harmonization, transformation. An image illustrating how data is transformed into the OMOP common format within the NCATS Secure Cloud Staging area. On the left, a figure labeled Reincarnate CDM Instance is next to an arrow, which points to the right. Inside the arrow is the Adeptia logo and the text Commercial ETL tool purchased by NCATS. To the right of the arrow is a figure labeled OMOP. Above that figure is the Odyssey logo. Text below the image reads, Second stage ingestion. Repair or encode aberrant data. COVID LOINC codes. Transform source CDM into OMOP 5.3. Leverage library of validated CDM to OMOP maps.
The reconstituted data is then moved through the Adeptia pipeline to do the formal transformation from the source data models into our target data model, which in this case is OMOP 5.3.1. At the same time, we correct data that might be incomplete in terms of LOINC codes or other content that needs to be transformed into formal structures in the OMOP model. All of this work is done on the NCATS Secure Cloud staging area.
Slide heading: Data harmonization, integration. An image illustrating how data is merged into the combined data hub within the NCATS Secure Cloud Staging area. A figure on the left is labeled Contributed Hub Data as OMOP databases. It is next to an arrow that is pointing to the right and labeled Merge. To the right of the arrow, showing the output of the merge, is a figure labeled Combined Hub Data as an OMOP 5.3 instance. Around that figure are logos for FedRAMP, Palantir, and AWS GovCloud. Text below the image reads, Final merge. OMOP version data from all sources will be combined into analytic database. Analytic database will migrate to Palantir Analytic Platform.
Once we have the reconstituted data, we can then merge it into the common OMOP file master that is periodically moved into the Palantir environment. Palantir environment is on the AWS GovCloud. It is FedRAMP certified and FISMA moderate in terms of security, layers, and confidentiality. No data that is on the Palantir environment can be downloaded, and limited data sets cannot even be viewed by individuals, but only by software agents.
A dashboard in the live Palantir environment shows key statistics, including COVID-19 positive patients, total patients, sites signed DTA, sites data ingested, rows of data, procedures, lab results, visits, observations, and drug exposures.
We are now live in the Palantir environment with real-time data. As you can see, only 3 sites have been ingested at this time, despite 26 sites having signed the data transfer agreements. Thus, the data we're demonstrating today is relatively small. Nevertheless, this will constitute the largest collection of row-level data in the United States on COVID-level patients. That will allow unprecedented analytics, specifically machine learning, in a manner that is not possible with federated systems that are currently used in many environments. These systems are not competing, they complement each other significantly, and we believe that the contributions of machine learning from the N3C data support will enable discovery of information and knowledge not easily discovered through other mechanisms. As we move down, we can see that there are manners of being able to visualize the cohort.
The presenter scrolls down to show data for cohort demographic characteristics, including gender, age, and race for COVID and non-COVID patients. On the left, the data appear in table. On the right, the data for age are displayed as a bar graph.
Specifically in the context of bar graphs and visualizations of information that is shown in tabular renderings. We can toggle between these bar graphs to show and visualize any information that might be relevant to the investigator for a particular cohort.
A map shows the distribution of COVID-19 hospital visits, represented by dots in the St. Louis region. A slider at the top of the page tracks the number of days past January 1st, 2020.
This is the time-space analytics associated with the limited data set that includes 5-digit zip code and real date times. As you can see, as the bar graph move, we can see a spread of COVID throughout the St. Louis region in this particular illustration.
The presenter moves the slider to the right, showing time elapsing since January 1st, 2020, and more dots appear on the map.
Each of these dots represents an aggregation of patients around a town centroid, or eventually a zip code level of information, and is connected to the underlying electronic medical record. Thus, we are able to predict spread and epidemiologic patterns associated with electronic medical records as predictors.
An interactive figure displays data access privileges for specific users. Different data tables are represented by boxes, which are joined by thin lines to form a large network. The color of each box indicates whether a user has access privileges.
This illustrates the permissioning capability of the underlying Palantir environment. Each of these little boxes constitutes a data table with associated code to derive it, and the colors illustrate access privileges. On the left, we can see red data that is restricted, that constitutes the raw limited data set, whereas the blue data for this particular user shows what they are authorized to access downstream to avoid direct personal access of the limited data set.
The presenter opens a drop-down list of users. As various users are selected, boxes in the figure change color, indicating that users have different access privileges.
These are configurable, so we can see that other users have different combinations or permutations of permission and access. This would be configured depending upon the analysis that an investigator seeks to perform, and anybody can apply to become an investigator after signing the data use agreement and the code of behavior for the underlying access to the data. As you can see, some users do have access to the complete data for management and maintenance purposes.
A chart showing an analysis of ventilator support requirements.
This illustrates an analysis on a small sample of data for demonstration. This is ventilator support requirements, and you can see that there are reasonable emerging data from this random forest analysis showing respirations, pulse oximetry, and related measures that are plausible in the context of predicting ventilator support.
A principal component analysis, PCA Plot, with a slightly higher density of 0 ventilator data points appearing on the right, and a slightly higher density of 1 ventilator data points appearing on the left.
The underlying PCA plot does show some discrimination, even though this data set is relatively small for illustration purposes, that can distinguish between groups or aggregations of patients and their risk of ventilator requirement.
A receiver operating characteristic, ROC graph. The ROC curve is jagged but has a reasonable separation from the reference line.
The ROC curve correspondingly, while jagged, showing small numbers, is respectable, showing an ROC curve of 0.85. And these numbers, of course, would be greatly enhanced by the aggregation or the contribution of additional data sites to increase the power, precision, and capabilities of machine learning tools and resources on the N3C environment.
Dr. Rudder speaks on her porch.
The platform will be open to all approved users, and for more information about N3C and about how to contribute data or how to access and use the data, please go to the NCATS website, which will have the most up-to-date information. That's ncats.nih.gov/N3C.